Okay, so when we did the momentum chapter, we kind of skipped the very end of that chapter, which describes the rocket equation. And it's very interesting, actually, problem, especially when in modern times we are focusing on space and putting satellites in orbit or going to Mars, for example. So it's a momentum problem. So what you have here initially is that a rocket is traveling. It has a mass m and a velocity v. Well, my rocket looks like a fish over here, but that's all right. Um, so the momentum here, of course, is your initial momentum is mass times velocity is mv. And then to increase its velocity, it actually burns fuel and puts this fuel to the back of the rocket. And as the fuel exits the rocket, it actually gives a kick to the forward motion of the rocket. So we can think of, let me just erase this a little bit. It looks more and more like a fish, but I should be more diligent about it and maybe really maybe make it look like a rocket, okay? Something like that. So what happens here is it ejects dm mass, which is the fuel, from the backside, okay? But so the rocket ejects dm mass, and there's the fuel from the back. But what is important here is that we're going to take the dm to be negative, and that's because of the calculus that we're going to do right now. So make sure that dm is negative. Actually, if it is positive, our calculation will not work out. So once it ejects dm, what is left over is, of course, you have to subtract the dm off from the main mass. But because it's negative, what the rocket now has is m plus dm, because dm itself is negative, okay? Let's say it's minus 10 kilogram or 100 kilogram, whatever it is. So because it's minus, so you just put that plus sign in there. That's really important. So, and because it has ejected the dm, it now has a velocity. It gets an extra velocity, which is dv right there. Okay, so the rocket is now moving forward with the mass of m plus dm and with the velocity of v plus dv. And the ejected material that went behind is dm, and then its velocity is the exhaust velocity. We call it vex. So vex is the exhaust velocity. Okay, but what is vex? Remember, it also has the velocity of the rocket, right? Because it's moving with the rocket. So the v exhaust velocity is with respect to the rocket. This is with respect to the rocket, right? But the dm will have velocity v minus vex velocity. That's what I wanted to say, right? Because the dm was traveling with v already, and then you have vex, which kind of that's with respect to the rocket. So you have to kind of subtract off. Okay, so what's my pi? Pi initially is mass times velocity of the rocket moving initially like that, equal to, let's look at over here. We have that main rocket mass, m plus dm, and it's now moving with v plus dv. But then I need to take into account this guy, dm and vex. So, but it would be all negative, right? So what I am writing is minus dm because it's going to the left hand side, times this right here, v minus vex, right? Because remember that vex is with respect to the rocket, but we need with respect to the laboratory system, like we are looking at it from our vantage point of view, because this dm will, as the rocket moves, the dm is kind of have the initial velocity of the rocket, and you have to kind of subtract off the vex. Initially, that this guy will go to the left, but as the rocket velocity increases more and more, this dm with respect to the rocket will move backward, but with respect to us, will be moving together with the rocket to the right hand side as the velocity of the rocket increases. So let's open this up. Let's see what we get here. We get mv is mv plus mdv plus vdm, I'm just multiplying it through, plus dmdv. Okay, and then I have these two right here, minus vdm plus v exhaust dm. A number of terms. Let's see which terms we can cancel out. Okay, so my mv cancels out, which is great, and then vdm plus vdm and minus vdm cancels out, and we're left with three terms: mass of the rocket times that increase in velocity dv, the dm, that's the amount of mass which was ejected from the backside, times the velocity increase, plus the exhaust velocity times the mass of the fuel that is ejected. Okay, so now let me erase this part. Okay, so let's see what you get. I have mdv, dmdv, vex dm. So what I'm going to do is that I'm going to keep mdv on one side. So it follows from there. mdv equals minus vex dm minus dm dv. So to make our calculation easier, we're going to ignore this part right here, dm dv, because both are a small mass and a small velocity. So they would be, we're going to consider them as zero. Just, it's really not zero, but we're going to ignore it for the calculation. So right now what you have is, this is my result actually. mdv is minus vex dm. All right. So we can do several things with them. Okay. One of them would be, I can figure out how the velocity changes with respect to mass of the rocket, because as the velocity increases, the mass of the rocket becomes smaller and smaller, right? So you can see we can do a separation of variable here and get that. So what's the separation of variable? We can get dv over here. On this side, vex dm over m. Okay, so and then we just do an integration. We want to go from certain initial velocity v naught to v, and here we want to remember vex is constant. We want to go from some initial mass to the present mass. You know, it's like if you send your rocket with 1,000 kilogram and then it's only 100 kilogram, let's say, and then the velocity initially could be 0 and going to the final velocity that we want. So what do you get here? You get v minus v naught minus vex. I get log. So also change the variable so that we can integrate over that and put the final limits on it. So what's the log? Log would be, simply going from some initial mass to final mass, right? Okay, so that's that, and then I can rewrite it such a way that v equals v naught plus vex. If I want to make this positive, I can put m naught on the top, m on the bottom, then this becomes positive. So I can write like that. So that's one of my initial equation. This is also rocket equation. And if I want to do a very quick calculation, saying that let's say you're, I'll just make some arbitrary exhaust velocity. Say your exhaust velocity is 4,000 meters per second. You need such high velocity, that's 4 kilometers per second, to make this rocket to go anywhere, actually, to get to very high speed. You want 10 kilometers per second, 11 kilometers per second rocket speed if you want to go, towards Jupiter or wherever. So you have 4,000 meters per second, let's say. And let's say I want the rocket to achieve a velocity of 10,000 meters per second, okay? Let's say from zero velocity. It's more an ideal scenario, but let's say, so what should be my log m naught over m in that situation? So you can see right away that log m naught over m will be 10,000 over 4,000. Okay, so that's 2.5. That's 2.5. So what's log of x is 2.5. What's m naught over m? Well, in this case, m naught over m would be e to the power 2.5, right? E to the power 2.5, right? So so that's basically the fraction. Okay, that's the fraction. So what's e to the power 2.5? So let me find out very quickly. If I can find my calculator. Okay, so I would have e to the 2.5 to the power is 12.2. Okay, what's 12.2? That means that whatever is the leftover for mass, if you multiply that 12.2, you get the main mass, right? So, or the other way of writing it would be m over m naught is 1 over m. So what I want to do is that basically I want to multiply it by 1 over 12 point, sorry, not I want to take that fraction. So 1 over 12.2 is 0.081. Okay, 0.081. So what does that mean? It basically means that the fraction that the mass, the original mass is only, if it is 100%, then it only 8% will be left after you exhaust the fuel, right? So that means that 92% of the rocket would be fuel. And after, you would need to actually exhaust 92% to go from 4,000 meter per second to 10,000 meter per second. That's how much. So the main portion of the rocket would be simply the mass of the fuel itself. So that's quite incredible, actually, when you take a look at that, right? So keep that in mind. So let me look at a few other things. We can do a couple of more things with it. I want to rewrite this slightly differently. That means that I can take this equation again. Okay. Let me take that equation again, which is V equals V naught plus VEX log of m naught over m, right? And you can also write it out as V minus V naught equal VEX log of m naught over m, or you can V minus V naught over VEX log of m naught over m, V minus V naught over VEX I'm just going to take the exponential of it. So I can put a negative in here, and I can write log of m over m naught. Okay, so you can see right away what the situation is. M over m naught equals e to the power minus v naught over vx. So m would be simply m naught e to the power minus v over vex. We're saying the same thing, but now what you have is an exponential form of that. So whatever mass will be left behind if you do this. So we can do this way is m over m naught. And remember what we wanted. We wanted to go up to 10,000 over 4,000, and we should be getting the same thing. So what is e to the power minus 2.5? So 2.5 minus, I take the exponential, is 0.08. So m is m naught times 0.08. Okay. So what does that mean? It means that if your m naught is, let's say, 100 kilogram, and what will be left at the end would be only 8 kilogram. So you have actually exhausted 92% of the mass of the rocket, which will be in fuel. So this is one part, and you can also find out the force and acceleration from these equations. So let me quickly look that up. So remember what we had after we had PCOM, principle of conservation of momentum. We got PI over PF, and then we proved m dv equals minus VEX dm. Remember we did that. So I can divide both sides by this, right? And then what you get is that you have MA equals minus VEX dm over dt. dm over dt is actually your rate of fuel exhaustion, right? How fast you're burning your fuel. So you can see this is force equals. So I can get a force just from that. If you know dm over dt, that will be kilogram over second. Or I can write acceleration itself as minus Vx over a dm over dt. Okay, that's m, right? M. So for example, we wanted the exhaust to be 4,000 meter per second, right? And let's say dm over dt, it depends on the rocket and it should be given. And let's say dm over dt is somehow your, every time you take the mass, original mass divided by 120, or 100, let's say, I'm making it easier, let me say 100, so it would be 100. So this would be per second, okay? This would be per second, whatever is happening, this kilogram per second or whatever it is. So if you plug this in here, what I can get is minus Vx over m, and this would be m over 100, okay? M cancels out, it will be 4,000 over 100, so that's 40 meter per second square, okay? So so anyway, take a look at that, the examples that goes after the momentum calculation at the end of this chapter, and I will see you in class. Okay, thank you.